Welcome to the next video on mathematical logic. Still talking about the syntax of propositional logic. In this video, we are going to introduce the idea of induction on complexity and prove its validity. As warm-up to talking about induction on complexity, let's actually just start by thinking about how we could use, in this particular setting, regular induction. In what we'll often be interested in doing is having some property, call it P, which is a property of sentences, right? So it makes sense to talk about whether a given sentence does or does not have this property P. Just to give an example of such a property, we could say that P of X means X is a sentence letter or leads with a connective. So that's just for the sake of giving something concrete, just so you see the kind of thing that we're calling a property. But anyway, this particular example, it's clear that every sentence has this property, but we'd maybe like to prove that rigorously, perhaps. So one way you could approach that is by using regular induction, right? Have an index, indexed family of sets or objects or whatever, and prove that our particular claim holds for the base case, and also if it holds for some non-negative integer n, then it also holds for n plus 1, right? And that technique would work here, talking about the property holding for every element of cent 0, and then also showing that if it holds for every element of cent n, then it also holds for every element of cent n plus 1. So that is how we could use regular induction to prove something like that. But there is a nicer way, right? You know, it's completely doing the same thing, but just kind of cutting out some of the features that seem to recur over and over as you use induction in this particular setting. And that is, rather than starting off with an index like n and looking at the base case where n is equal to 0, we know that in every situation, when we're setting n equal to 0, we're talking about cent 0. And that's just the same thing as the sentence symbols. What we could do is just jump straight to that, right? We could say, suppose that you have a property which holds for every sentence symbol. And then likewise in the inductive case, right, rather than talking about, you know, if every sentence in cent n has this property, then every sentence in cent n plus 1 also has this property. We could just jump right into grabbing some sentence, right? And that sentence must have some complexity. And so what we would, you know, argue is that no matter which one you take, we assume that the property holds for that sentence, and then show that it also holds for a sentence one increment more complex. That is to say, show that, you know, its negation also has that property. And then also that the property is preserved under taking the various binary connectives as well. So anyway, so this is essentially just doing regular induction, but kind of cleaned up for the things that seem to occur over and over when we use it in this particular setting. Yeah, right, that was a whole bunch of kind of conversation about this idea. But here we'll formally state, and then on the next slide rigorously prove, the validity of this claim. So the formal statement of what I've been saying so far is that we take P to be any property which is well defined for sentences. Suppose that P holds for every sentence symbol and also is preserved under taking connectives. And when I say preserved under taking connectives, what I mean is just what's written right here as number 2, right? So if phi has it, then so does negation phi. And if phi and psi have this property P, then so does bullet phi psi, where bullet is any one of the binary connectives, right? So clause 2 here is what I call the property P being preserved under taking connectives. So if P has these two properties, right? It holds for all the sentence symbols and also is preserved under taking connectives. Then I claim that every sentence has property P. We will prove this, and we will prove it by induction. Now, the way that I'm structuring this is not exactly the same way that the textbook structures it, the one by Hinman that all of this is based on, although the difference really is quite small, right? In a way, Hinman kind of packs this claim into the lemma that comes before this, and then just indicates that the proof is relatively simple by induction. So here I'm going to just do the proof by induction. In his textbook, this is, you know, a proposition that he basically says is an immediate consequence of the lemma. I'm doing it differently. I'm proving it directly. So, right, if I want to prove that a property P satisfying those assumptions must hold for every sentence, and I suggest that, you know, clearly it's enough to prove that the property holds for every non-negative integer n and a phi in sent n, because every sentence is like that. So I'm going to prove this by induction on n, right? So in a sense, kind of what's happening is that I'm going to use regular induction because we know that it's valid to prove this theorem, and then from now on, I no longer have to, you know, directly use proof by regular induction. I can instead use this somewhat more simple, elegant proof by induction on complexity. Anyway, so this proof is by regular induction, though. So anyway, so we're going to address the base case, which of course is n equal to 0, and that means that we are trying to prove that the property P holds for every sentence in sent 0. But that's just immediate, right? Because we assumed in the assumptions for this claim, we assume that P holds for every sentence symbol, so there's really nothing to prove at this point. Now we go to the inductive case. So we're going to let n be any non-negative integer such that every sentence in sent n has the property P. And we're going to claim that it must follow that every element of sent n plus 1 also has property P. We're going to prove that by, find a conditional proof. So we're going to assume that every element of sent n has property P. We, again, want to prove from that every element of sent n plus 1 also has property P. So we're going to take an element out of sent n plus 1, call it phi, and we're going to prove that it has property P. We have this phi in sent n plus 1. Now, kind of like in a previous proof, there are going to be 3 cases. Either phi is going to be in sent n, or phi is going to be in negation sent n, or phi is going to be in bullet sent n, where again bullet refers or could take any of conjunction, disjunction, conditional, biconditional. Let's consider the first of those cases, which is that phi is in sent n. Well, as we've already said, in the inductive hypothesis, we are assuming that every element of sent n has property P, so nothing to prove here. Now consider the next case where phi is in negation sent n. Then we're going to claim that, therefore, phi has property P. So that's going to be a conditional proof. So we assume that phi is in sent n for conditional proof, or sorry, negation sent n. And okay, well, what's just the immediate consequence of that fact? Well, there must exist some psi in cent n such that phi is negation psi. That's just the definition of phi being in negation cent n. Okay. Now phi is in cent n, therefore phi has property p. Also, p was assumed to be preserved under taking connectives, and in particular, negation, as we have here. So, since psi has property p, and phi is negation psi, and p is preserved under taking negations, then phi has property p. And that's exactly what we wanted to prove this whole time, in this particular case of considering phi in negation cent n. So we're done with that case. And as I often do, right, because dealing with a binary connective is almost identical in this particular problem or proof to what we did in the negation proof, then I'm not even going to bother with it, right? The minor changes to what we did for negation would complete the proof for the binary connectives. So now that's all three cases, right? That's cent n, negation cent n, and bullet cent n, cent n. So that's all three cases. So in every case, phi has property p, and that's exactly what we wanted to prove for the inductive case, right? So we're now done with the inductive case, therefore we're done with the proof by induction, which means we're done with the whole proof.